We have a problem with the dreaded pluralization of the terms coordinate and tangent line. I didn't like that when I was a math student because it left the door wide open for more than one answer, so I didn't care too much for it. But anyway, horizontal tangent lines are important because if you have a max here, there's a horizontal tangent line that indicates the max. In the very same way, you have a horizontal tangent line that indicates a minimum value. So you can use either the second derivative test or the first derivative test to determine, without seeing the graph, whether or not the horizontal tangent line corresponds to a max or a min. But we're not too worried about that here. We have an expression, and I'm not so sure the integers are important here. It could probably just be positive real numbers greater than 1. I don't even know why I put integers there, actually, come to think of it. But in any event, the rest of the problem will proceed kind of routinely, I guess. We can use what I call standard calculus. That is the quotient rule, which is what this is. We're invoking the quotient rule. I'll abbreviate that. Quotient rule because it's the derivative of a rational function. Not a rational function, but a quotient, right? Now, I always remembered it by saying the derivative of the denominator, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Some people would remember it as the bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. Okay, so that's a mnemonic. It's a mouthful. But anyway, the quotient rule is a little bit harder than the product rule in terms of remembering it in the concomitant algebra. Now, it's important to factor this so when we set it, it's easier to set it equal to 0. And again, y'all, each of these have slopes m equals 0, right? And the derivative is a formula that finds the slope of the tangent line to a function at any point on the graph of that function where not always, but sometimes it's undefined. But the same thing right down here, m equals 0, right? So that's the 0 right here that motivates this 0, okay? So again, setting something equal to 0 is much easier to do once you get it in factored form, and that's what I've done down here. Now notice that this piece right here, just this denominator and this numerator are always positive. This part right here is greater than 0 because it's an exponential, right? And then this part clearly is greater than 0 because it's an exponential, which is positive plus 1, and it's squared, so it's positive like crazy, right? So the only thing we really have to worry about, the only live piece, is this green part here, okay? And it's really fairly easy to work with this. You can see the way we got this very quickly. Subtract a, that gives you the minus a right here, divide by this parenthetical expression a minus b, and then extract the bth root, okay? And so what I've done here is just an example. So this we've gotten it in terms of a and b. We've gotten x in terms of a and b, which makes quite a bit of sense as far as the original problem. The original problem did have, you can think of a and b as integer parameters or just positive real number parameters. And so we found the x coordinate of where the horizontal tangent line would occur. Okay, in other words, each of these have x coordinates, and this is the x coordinate where this is what it would be in terms of a and b. Okay. Now I just used a concrete example here. Oh, y'all, I better mention one more thing. Observe that f prime at 0. This is going to be a free horizontal tangent line. Okay, it always happens right here because you see the factored form. If x is 0, this whole part's equal to 0 no matter what's going on over here or down here, right? So f prime at 0 is the location of a horizontal tangent line, okay? So in other words, the location of a horizontal tangent line would be 0, comma f at 0, okay? Always, for any of these, independent of a and b, okay? But what I did is I just picked one right here where, and I didn't graph it myself, but I did one where, let's see, what do we got here? A would be 4. And B would be 3. I just picked this arbitrary. It's just an example, folks. And you get this value here, the cubed root, just by directly using this, okay, just substituting in, right? Okay, and you get this. And this is approximately lazy equal sign, maybe minus 1.6, I think, roughly to the nearest tenth, I think. I can't remember exactly. It's not exactly 1.6. But in any event, what I did, I got Desmos to graph this. And here it is right in here, folks. You can see the 4 and the 3 right here. And look there, that sure does look pretty close to minus 1.6. See how you have this horizontal tangent line right here? Let me see if I can manage to draw that. Okay, horizontal. And of course, there's the one at 0 right there I told you about. It's going to always happen. But you see there, the scales here is minus 1, minus 2, minus 3, minus 4, minus 5. And so this minus 1.6 looking pretty good right here, right? So you see this minus 1.6 is definitely the x-coordinate associated with this horizontal tangent line. So it does work, and that's it. This is our example. I guess that's all I have for you right here. I probably could have shown a little bit more work on the algebra side of the quotient rule, but I just you can check. I'm pretty sure I got it right because this checked out when we got x isolated. Okay, so that's all. We are done.